Hello, everybody. Welcome to TechLunch. Thank you. We're going to get started in just a minute, so if you could finish grabbing your sandwiches and everything and find a place to sit or stand. So my name is Aoife. I'm a software engineer here at Algolia. Thanks, Toby. And is it anybody's first time visiting Algolia today? Okay, good number. Welcome. Welcome to the new people and welcome back to everybody else. What about TechLunch? Has anybody come before for TechLunch? Okay, all right, good. Glad to see you back here again. Something went dark. Okay, we can do this. All right. So TechLunch is something that we do once a month here at Algolia. It's the last Wednesday of every month. So it's 12 to 2. We always have 3 lightning talks and lunch, obviously. So what is Algolia? I'm sure most of you here probably know what Algolia is already, but just in case there's some people who don't. Algolia is a hosted search API. Basically, we make it really quick and easy to implement very fast, powerful, and relevant search into your website or application. Thousands of companies are using Algolia around the world today. So you may have used Algolia and not even realized you were using it. We have e-commerce websites like Birchbox and the Couples using it. Media websites like Twitch and Medium. So you may have seen us around and not even known it. So that's what we do here. Today we have 3 speakers for you, as I mentioned. The first is by our very own co-founder and CTO, Julien Lemoine, who's going to talk today about the distributed architecture of our search API. We also have Romuald Carry from the Vialet, who's going to talk about the Vialet Phantom, a multi-room distributed system. And Alban Derek Bourg, sorry, I'm doing my best, from Criteo, who's going to talk about client-side load balancing. So without further ado, we'll get right into the first talk with Julien. So if you could give him a nice warm welcome. Thank you.
Okay. Just a question, who didn't get a sandwich or a salad? 1, 2. We'll try to bring more for during the event.
Is it? Yeah. Good. So thanks everyone for coming. So I'm Julien, co-founder and CTO of Algolia, and I will try to give a very short and not too deep introduction about our distributed infrastructure. But before going into the detail, I wanted to share a few up-to-date numbers. I know everyone likes numbers. So in terms of usage, today we have a bit more than 5,000 customers over more than 100 countries, and they perform every month more than 160 billion API calls. Around 25% are search API calls. So it might be surprising, but the big majority is actually indexing operation. Every time a data change, every time there is something that changes in the data set, we have an API call to update the data. That's the big majority of API call. And we will discuss about read, write operation a bit later. So keep in mind that write operation is actually pretty massive. In average, it represents above 10 gigabits of traffic, internet traffic, and 20,000 queries per second. It's an average. So of course, in terms of spike, there is pretty massive spikes. The last one I remember was 500,000 queries per second, like a few months ago. And of course, we need a pretty big infrastructure to handle such a volume. So we have more than 1,000 servers distributed over more than 60 data centers. And of course, it took us time to get there. It's not something that happened in one day. But the early investment in the distributed infrastructure definitely helped us to get there. So scaling is one thing, but being highly available is even more important. So I'm sure a lot of you already heard about the CAP theorem, which is you can only have two of the three following concepts: consistency, availability, and partition tolerance. This theorem is true for us too. So consistency, it means that every node has exactly the same state at every moment. Most of the time, it means that you have consistency when every node has the last write operation that was performed. Availability means that the system is always available, of course, but that every node which is not failing has a coherent answer. And partition tolerance is really key when you are distributed. It means that you can tolerate to have a split, like some machine that cannot communicate between them. So for us, it's true too. We cannot do any compromise on availability, for sure. It's too critical for an API. Partition tolerance, we cannot tolerate anything on this one too, because we want to use several providers. I will give a bit more details, and we are distributed worldwide. So partition split happen nearly all the time. So only one that remains is consistency, and we have done a compromise. We are eventually consistent, which means that at a given moment, machines can have a different state, but we ensure every machine will have the same final state. And I will give a few examples to make it more concrete. And if you have to keep only one concept about our architecture, we have a unique mix of multi and mono-tenant. Our infrastructure is divided in clusters. A cluster is a minimum of 3 machines. And every machine has 100% of the data. So it's like a complete set of replicas. Every machine accepts all read and write operations. So it's like a small set of machines, and we can add more. I will give more examples. Those clusters can be configured as a multi-tenant. We have several applications on the same cluster, or as a mono-tenant. Only one application, only one customer on a cluster. And it's critical to have both. Multi-tenant is critical to be able to offer low-end tier, like we have a free plan with 10,000. If we have a dedicated cluster for a free plan, it's like a no-go. But a dedicated instance is critical to be able to guarantee performance for our customer and to be able to comply with the most strict regulation. So both are actually critical. And I'm convinced like most of the SaaS applications in the future will have such a mix. One of the small bonuses is that we have developed an API to migrate application from one cluster to another. It's pretty useful. So coming back to high availability, we have 2 different types of operation, write and reads. For read operation, it's mainly searches. And it's actually the easiest one to scale. As all the machines have 100% of a data set, any machine can answer a search query. It's a local operation. There is no inter-machine communication. So we just need to replicate and add as many machines as we need for high availability and for scalability. So if one machine is down, the 2 others can handle the load. And if even 2 machines are down, the 3rd one can handle the search operation. But for write operation, it's a bit more complex. Any machine can accept a write, an update. So we need to have like a coherence between the machine. We need to have something that ensure we will apply exactly the same order on every machine. We need to basically order all those indexing operations. We need to have only one order. And to do that, we use a distributed consensus. That's the only system that can allow us to have such a unique order. So we use the Raft algorithm. It's one of the most common. Paxos is another one, but we use Raft for simplicity. And every write operation uses such a consensus to be able to have like a unique sequence. In the following diagram, you can see that we use several data centers, several providers, like we have different autonomous systems, different network links. Most of the time using 2, but we even have an option to have 3 different ones, but we always distribute a cluster in one region. So it means we have a low latency between the different nodes, which is super important for the consensus because we have a lot of intermachine communication. Let's take a very concrete example. So like you can see on the left the time, first one and last one. And we can see 5 indexing operations received on the 3 different nodes. Every time a node received an indexing operation, it forwards the operation to a leader. We have an election algorithm that ensures we have only one leader at one time. This leader will launch a consensus algorithm. And as an output, we will have just an integer. It's a sequence. The first job got the integer 1, and so on. We have another good properties with such system. We guarantee to never have a missing number. It's a sequence that increases over time, but there is no missing number, which means that when a machine is done and it comes back to life, we can ensure that we can wait for the missing job before starting over indexing. This one is an example of the eventual consistency. In the following diagram, you see that the node 3 is done at one specific moment, maybe an hardware failure. But during this moment, we still receive indexing operation. And that's the high availability part. We want to be able to tolerate a failure. With the size of our infrastructure, we have failure like every day. We always have at least one machine down. And we want to continue to index. So if you look at T1, just after the machine come back to life, we have a different state. The machine 1 and 2 have exactly the same state, but the machine 3 is basically, there is some delay on this machine. But if we look at T2, like a bit further, we have exactly the same state on all the machines, because the third machine has catch up. So this is why we need to have such an eventual consistent model to be able to tolerate downtime. This one is a bit simplified. In practice, it's a bit more complex. We have, of course, some parallelism on machines. So we add the sequence in a scheduler, and the scheduler executes job in parallel. So if we are on a multi-tenant setup, we execute different application ID in parallel. But if we are in a mono-tenant setup, we execute and we index different shards, for example, of one index in parallel. And this is the system we use to distribute the search worldwide. We take the sequence and we distribute the sequence worldwide. So in this setup, we can see that we have a primary cluster in US Central, and this is the 3 machine with the consensus, and this is the responsibility of the cluster to have one sequence. And then we have some replicas worldwide. It can be only one machine, and we basically send the sequence to those machines. So those machines will have exactly the same sequence, the same result at the end. But at one specific moment, it's very common to have a different state, just because there is different latency, and worldwide we have a different speed, different bandwidth between locations. This one is pretty unique for 2 reasons. It's really different than what you can see in a CDN. We proactively send all the operations to the different location. It's not a reactive system where you fetch the result on the primary location. And it gives us the ability to have like one specific setup per user. We don't need to have all the locations for all users because it has a direct impact on the cost. The last missing part is how we redirect the user to the location. Of course, we need a way to redirect them to the closest location. And we use the DNS for that. The DNS is what translates a domain name in an IP address. And we use the geo IP of the user. So we are using an Anycast DNS provider, and we translate the name, the application ID in the closest IP. And as it's an application ID, every application ID can have a different set of data center. We have 16 regions in total today, but every user can select the location that makes sense for them. We don't force them to use like all the regions we have because the cost will be massive. Like multiplied by 16, the cost of the search is a pretty big consequence. Last thing you might have in mind, everything is fine until everything can fit on one machine. because that's what I said, like every machine of the cluster has a whole copy of the data. So especially in SaaS, like it's a never, it's a always increasing data set. It's never stop. It's just a question of time before it won't be able to fit on one machine. So we need a system to be able to grow over several clusters. That's what we have developed with multi-cluster, and it's very different than what you can find in the different engine. Basically, what we ask to our user is to have a key, a shard key, to split their big data set in several pieces. In SaaS, most of the time, it's a user ID. Every user of the SaaS application will have an ID, and we will split the big SaaS use case per user. And we will expose them like a way to host one user on one cluster. And there is a shared mapping between all the machines of all clusters. And we expose an API to move one user from one cluster to another. So let's say, for example, you are an international SaaS company, you have different regions because you are compliant with all regulations. So you have a data center in the US and one in Germany. By mistake, one of your users opened an account in the US instead of Germany, and they start to use your service. And you need to move the data back to Germany. Most of the time, it's a pain. And with this offer, it's only an API call. You just need, okay, I want to move this user from the US to Germany, and we don't cut search and API operation. So we handle all the transition states, and it's like completely invisible for you. And there is even more. We have an option to add and remove clusters. So we can add like new machines, new clusters to the pool of resource for the user. And then the user can decide to allocate the user as they want on those resources. Which means there is never like a big bang, which happens in most search engines. You have to reshard all your data, you have to reindex everything, because in most solutions, the number of shards is static at the configuration. Like if you take an Elasticsearch, you need to configure the number of shards when you install your setup. So this offer is pretty unique for SaaS company to be able to scale over time and avoid like any big bang in the system that will take a lot of resources. So this is a very short overview of what we have in terms of infrastructure. Of course, it's simplified. There is a lot of very deep and complex like way to implement such a system. We have quite a lot of content already available in like, for example, high scalability. And if you have any questions, feel free to ask. I would be happy to give more details. Thank you.
Are there any questions? Okay. So you know how to use the catch box, but for everyone else, this is a microphone, so try to speak into it.
Thank you, Julien. Could you remind me what happens when in a cluster every server is accessible from the outside world, but they cannot communicate into each other? So how does the consensus work in that case?
So there is a lot of situation when, like for example, like we have 3 machines, 2 data centers. So the data centers are available from the outside, both, but we cannot communicate between them. So in this case, we have a partition split. We have 2 machines on one side that can communicate, and one which is like isolated. So during this moment, all indexing operations that will be received on the 2 machines will continue to be processed, because we will have like the consensus with 2 machines. So we need the majority of the machine to be able to accept the operation. But the one which is isolated won't be able to index. So this machine will be on the side until the link is available again, and then the machine will catch up.
Thanks.
Thank you very much, Julien. Quick question on DNS. You are mentioning you're using one DNS, but isn't that a bit risky? Do you consider using a secondary DNS at some point?
So we have several DNS providers, of course. At the beginning, we had only one, but it's a big stuff. So we have one DNS, which is like doing the geo redirection, but then we have a fallback on another domain. So we have algolia.net as the first domain, but that we have algolianet.com, which is a fallback domain hosted on a different DNS.
Okay.
And all the logic is done at a high level in the API client, and we have a complete retry on a complete different system.
Okay, makes sense. Thank you.
Hey, I'm wondering what kind of tool do you use to test things in between clusters? Like, you want to take down some cluster, or how do you test that? Like,
So in terms of testing, I would say that the biggest test we have is that we have an infrastructure deployed on a lot of data centers, so we have failure all the time. So that's a pretty big one.
production is not a testing environment.
At the beginning, I remember the first version that I developed before having like any infrastructure and anything. It was more a monkey testing approach. So I had the software running for days, and I was killing like process in a random way, just to make sure we would be able to reproduce like all the situation. But in practice, there is so much variety in the different type of problem we can have. Like, it's not always a clear cut. Sometimes it's just that the bandwidth or the the bandwidth is divided by 10. Maybe the latency is increasing by 10. So there is a lot of degraded performance conditions, and those ones are the worst, because like a clear cut, it's always easy to reproduce and to have a good behavior. But when the setup is completely like degraded, what's happened? Do you have a weird case? And the best is to have like a lot of those cases all the time. But it's really difficult to have like, I would say, a complete test suite for all the situation, and we don't have one today, unfortunately. Like, we are not able to reproduce all the situation all the time. But I would say like the low-level layer don't evolve so much. Like the consensus algorithm, we have not done any modification since a while.
Thank you, Julien. I had a question about Raft. Did you implement it yourselves, or did you use a Raft implementation? And what monitoring do you have at the consensus layer? Are you able to monitor the consensus performance, consensus issues?
So it's a custom implementation. There are two reasons. The first one is that we implemented it like few weeks or months after the article was published. So at this moment, like, there were a very low amount of implementation. It was mainly, I think, one implementation, but it was like there were a big disclaimer: you should not use it in production. It's really to illustrate the article. So this is the main reason. And then I think it's one layer where we have to have some tooling around. So you need to have the complete control over it. So we have like everywhere in the software we have some probes, which is using our custom monitoring system. We are using a third party, but we have monitoring on a lot of situations. We have like people on call, and every time we discover something bad, we have people like handling the situation. So we have to have like special probes. Like, if the consensus is blocked for a specific amount of time, we have an alert, for example. Then we need to investigate: is it a network issue? Is it a software bug? Most of the time, it's more a network issue.
And you said that you implemented Raft just after the article, so before that you were using something else like Paxos and...
So I was starting to implement Paxos. So I am already used Paxos several times in the past, but it's a super tricky one. So when Raft was published, it was like a no-brainer. Like, if the implementation is easier, if it's easier to be like convinced your implementation is safe, I think it's easier. And then later on, when you need to explain, like if we had to go into the detail of explaining Raft, I'm pretty confident we can do it in a 15-minute talk. For Paxos, it's a bit more complex. I'm sure it's doable, but Paxos was developed by a mathematician, and let's say it was designed, it's super strong, it's super robust, but it was not designed to be easy to understand.
Thank you.
Thank you, Julien. I have a question about electing leaders. How does it work, and what's the algorithm behind it? Just the idea. Is it the same as Kafka or not? And what happens when you don't have a leader?
So, in terms of general concept, it's a token ring. So you have a ring of the three machines, and you have a token that turn between the machines. And of course, you have situations where you cannot have a leader. Like if you have 3 data centers, 3 machines, and every network link are cut, you cannot have a consensus. We cannot have a leader. So we cannot have like a leader, and the consensus is blocked. And like the indexing would be completely frozen in this case. So the principle is that you have a token that turns. You pass the token to your next neighbor, but if you cannot, you pass to the n+1. And there is a system that counts the number of people, number of machines that agree on this token, and the token is a proposal of leader. So it's pretty simple. It's described in the raft. Like most of the election algorithms are using the same concept, and it guarantees you have only one. And when you have a network split, you can have a network split by 2, by 3, by 4, if you have more and more machines. The algorithm is handling all the different cases where you have like a subset of the machine and pretty complex partition.
Okay.
All right, if there's no more questions,
Thanks.
All right, so next up we have Romuald Carry. So you can give him a little welcome. So. I can take that one. I'll take that out of your way. Got it? Take your time.
All right. Hi, everyone. My name is Romuald Carry. I'm a software architect at Devialet, and I'm here to talk today about the Devialet Phantom, which is this product right here, how it was implemented, and how it's a multi-room distributed system. So a few words about Devialet. Devialet is a French company founded in 2007. It started based on a major innovation in the way you amplify audio signals, a way to hybrid digital amplification and analog amplification. We created a bunch of other technologies afterwards, but our very first product was this. It was a very high-end audio amplifier, the Des Premiers, which was received with very raving reviews by audiophile magazines and audiophiles at large. So we worked on extending this amplifier range, basically, and we wanted to make our technologies available to as much people as possible, so we started working on Phantom, and we released a product in 2015. So Devialet Phantom, it's an all-in-one connected speaker, so it's what you would expect from a connected speaker. You can stream music from various online music services. It supports AirPlay, Spotify Connects, stuff like that. So from the very beginning, we wanted to have multiple modes of operations, which are illustrated on the slide here. So basically, you can use it as a single speaker. You just have one in your home, in your living room, for example, or you can pair 2 and use that as a stereo pair, left-right. But it's also a multi-room solution. So multi-room is basically you have different speakers in different rooms in your home, and you're able to stream music to a specific room or to play music throughout your house in a very synchronized way. So it supports multiple ways of connected to the network, and that will have some importance later. So we support Wi-Fi, PLC, which is basically networking through your power mains, and Ethernet. So when we started this project, we needed to decide how we would implement that. So we used microservices because all the cool kids were doing it. And so basically, all features in the product are implemented as microservices. So a quick example would be, in this system, you're going to have applications which are responsible for fetching music from the internet, and other applications are going to be in charge of ingesting this music and playing it on the actual device. So you have sources, which are the first ones, and the renderers. So the way we could have made that would have been to make a single application which would have gathered music from the internet and just stream it right out of the sound card on the device. But we wanted to have this separation, because if you have a stereo pair, for example, we don't want to have two applications producing audio at the same time and trying to synchronize them. It's much easier to have just one application getting the audio and streaming it to both speakers. So in that case, you'd have one source and two renderers, and each of those things are microservices. So it's really a one-size-fits-all abstraction. It's been really useful for us because, as I was saying, we have different modes of operation. So if you have a source and a renderer on the same machine, which is the case for Phantom, if you play some AirPlay on Phantom, for example, the source and the renderer are going to run on the same physical host. So we can scale this in different ways. We can run both services in the same process, if that's more efficient, if we have resource constraints or things like that. We can run that in two processes on the same machine, or we can run that across a network of Phantoms. So it has further some advantages for us. So we implemented all our applications as lightweight, single-threaded daemons. It's really useful because when you work in embedded, you don't necessarily have all the tooling you usually have on desktop. So for example, debugging on an application on a remote target, it's much harder than you'd expect. So if you're doing iPhone development, for example, Apple has packaged this in a really neat way, or Android, you use ADB, stuff like that. But when you're working on your own custom Linux distribution, it's much harder. So debugging remote single-threaded processes is much simpler. Moreover, it's usually just simpler to work mono-threaded code. We also have process isolation, and that's very useful as well. We could have built a single monolithic application running on each device, dealing with every aspect of the device, but any bugs, any hardware issue regarding a subsystem on the product could have caused the whole device to get offline. We'd have to start this application again. So we have process isolation, where basically each feature is hosted by a different process on the machine. That way, for example, if you have a crash of your Bluetooth module on your product, you don't have to take the whole device down. Only the Bluetooth part is going to be down. You can still play music. You can still receive music from another device. And it's also a very flexible design. One example is when we implemented Bluetooth in our product, because initially we didn't have Bluetooth. But when we added Bluetooth, we had to deal with two things. First, we had to get audio from Bluetooth. So we had to get the actual stream that your phone sends to the device. But we also had to deal with remote controls on the Bluetooth, on your Bluetooth phone, or even on our own Bluetooth remote. And so a remote is a service, and the source is another service. And we've been able to combine them in the same process because we had to share this Bluetooth device resource for which only one process can access at a time. And it also allows for very dynamic operations, which is very important for us. In most distributed systems, you usually have a set of requirements on what your what I call topology must be. You need to have at least 3 devices, and you need 2 to keep on moving forward. You need a majority and things like that. In our case, we can just say to our customers, oh, this is a very neat speaker, but you need 3 really to have it work in your house. So we had to work from 1 to many devices. So one aspect of distributed system in the way you interact between your devices. So most systems use a request type based of interactions, where basically it's a model of the web. You have a client which makes a request, the server processes it, and then sends you a response. We need something more because there's a lot of states that we needed to be aware about all around the system. So basically, our notion of a microservice is really a remote object. So a service instance is going to be very similar to an object instance, and an object has methods, but it also has notifications. So an object, a service, can spontaneously send a notification to all its clients saying some state has changed, something has happened, the user pressed play or pause or stuff like that, the volume raised up or went down. This is why we need those notifications. And we also have a property system where each object has basically a state that is immediately replicated to all the clients of this service. So as I said, we are doing mostly single-threaded development. So this required us to have an asynchronous API. We don't use blocking calls or anything like that, because anything you would do in that case, if it was on the same machine, you could do a synchronous call, just get the reply from the function you called and just move on with your life. But in our case, the call could be in the same process, in a different process on the same host, or even on the other side of the network. So we needed the API to reflect that. So the API, all our APIs, internal APIs, are asynchronous by default. And we built this framework on Protobuf. So Protobuf is a Google RPC foundation, I'd say. And they have a very neat way of describing services. We made some extensions to add the properties and notifications I talked about. But we derived our own compiler from Google's work. And we use raw TCP sockets as transport because HTTP did not allow us to have those notifications back. WebSockets now we're working on implementing our whole stack on WebSockets in the future. So we call that our RPC layer call me maybe, because when you deal with distributed systems in a home environment, it's really a maybe whether the call is going to go through or not, because users can do crazy things, and many different things can just break your network. An interesting example, we had issues, for example, customers or even us testing at home, we would have problems at some moments in our in using the product. And it would just be because you plugged in a vacuum cleaner or you turned on a lamp or stuff like that. And because we use PLC as a network way of exchanging data between the products, this can cause really important perturbations. You don't have those types, you have problems in data centers, but they're sort of well known. You can have loss of power, loss of connectivity, but in a home environment, really anything can happen. And it's really, really scary sometimes. Another part of working in a distributed environment, as I said, is we don't have DNS, we don't have things like that to find services, and we don't have an infrastructure on which we can rely to say, oh, I'm a service, I'm going to register to that subsystem, and that subsystem will make sure that everybody in the overall system knows I'm here and I exist. So the topology in our case is very dynamic. Our customers can turn on, turn off their product at any time, and we still want them to be able to use their products. So as I said, home networks are really unreliable. So we had to come up with a way to just figure out on a network what's there. So lucky enough, a home network is usually just a single broadcast domain. There's no routing involved talking between your phone and your speaker or your smart TV or anything like that. It's just one broadcast domain. So we could use a custom UDP broadcast protocol. And then we really split the notion of host discovery from service discovery, because we have a bunch of services running on each device. It can be on some device 50 or more, or it can be just five services, depending on what type of device you may have. So we needed a way to just not pollute the broadcast domain with never-ending broadcast messages in UDP for every single service that would announce itself on the network. So we have host discovery based on UDP, and then we have basically a daemon running on each host, which works as a registrar. So the registrar is in charge of getting the information from local processes, local to this host, that the services exist, what their endpoints are, everything like that. All the required information to announce this service to the world. And a public registry, which is basically the role of this daemon, is to announce to the rest of the world that those services are available on our local host. And one neat thing with that is because each process has to communicate locally with this WhatsApp daemon, if anything happens to one of those processes, it's going to be like a crash, for example. The operating system will do one really neat thing. It's going to close all its connections. And because those connections are closed locally to the host, the other end of the connection, which is the WhatsApp daemon, is going to be notified immediately that the service crashed or was terminated for whatever reason, and can propagate that throughout the network. So a device on the other end of the network doesn't have to wait for a timeout, for example, to figure out that something went wrong with the initial service. And so the final part on our end is how do you use those microservices, and how basically do you build your application on top of that? So our solution is to use aggregation. So basically any application running on any host, whether it's your phone or an actual device, is going to have an instantaneous view of what the world around it is. And it has to make the best of it. So if everything works perfectly, you just see every services on the network, and you can have a very neat user experience where every feature is available and the user can do anything and everything he wants. But at any time, any of the services can just disappear. So the application has to react to that and adapt itself. So that's what I'm saying with the dynamically adjust the behavior. And one important thing in our system as well is that the state is transient, which I mean, there's really little state that you actually have to save on disk, because it's basically the system is here, two speakers are grouped together, they can play together, but you don't have, I don't know, any data. You don't have to have strict consistency on most of the data that is exchanged in that network. So that's a very neat feature. However, some information is not transient. So typically network configuration, because if the device doesn't even know how to reach the network in the first place, there's no chance it's going to participate in the system. Things like API tokens. If a user logs in into his favorite music service, you don't want to keep his credentials, you just want to have an API token. So this API token has to be stored somewhere and distributed among the different speakers, because each speaker can individually go and play some Deezer or Spotify or whatever. And also one thing which is not transient is the way you configure your speakers. So basically if the user went through the process of configuring his system and making two speakers part of a stereo pair, he doesn't want, when one speaker goes down or when he unplugs the two and plugs them back in, to have two discrete speakers again and have to do the whole operation all over again. So this is also data which is not transient, and we have to share somehow in the system. So we do have flash storage on each device. It's basically a requirement if we want to store something on a device, like network configuration. But we also have issues that you don't have in a typical data center distributed environment. You don't have any reliable source of clock. So the local clocks on the device, we don't have an RTC, a real-time clock, so we don't keep track of the time if the product is not plugged into the mains on the power. We don't necessarily have access to NTP, Network Time Protocol, to synchronize with some time source, because we want the system to be able to work even though it's not connected to the internet. So that's our baseline. We don't have any guarantees on what the topology of the system is going to be. At some point, a user may have 10 speakers in his house, but just decide to have just 2 turn on even one. And in that case, how do you have a consistent write in that system? Because he could write to that device, the device could accept the write, and then he could turn this one off and turn another one on. And this new device has no idea what happened on the previous one. So you don't have any consistency for the user. And for like most people, this is really, there's no way they're going to understand that. It's very bad UX, and it's bad for a product like ours. And also, I said we don't have a requirement on the internet access. So a solution could have been to say, okay, we could create a user account and have some backend service, provide all this information. All the device would have to do is boot up, go to the internet, get its configuration, and move on. But we had a strong requirement not to require internet access. So we had to store some transient state in that system given those constraints. And so how do you do to avoid storage distribution? You just add a new box, and you make sure that this box is required and central to your whole system design. So it's an easy, it was really a quick win and easy solution. And it's not something that we want to use further in the future. You have to understand that when we started this project, it was a very small team. We had very strong time constraints, and we had to figure out how to do things. So we added a box, and this box is the convenient center of everything. So as soon as you have more than one phantom, this box is required, and it's going to be the place where you store all these states. And the system is not going to be available if this box is not available, and it's by definition a single point of failure. So this is something we're actively working on and making sure that we can provide compromises, I'd say, given our constraints. So this is a place where we store all the non-transient states. But it also has a very useful feature in most domestic environments. By default, there's no PLC networks in your house. Maybe if you use a Freebox, for example, they use PLC, but you can't, as a device, connect to that network. So you have to provide an extra network. And so the dialog does just that. It provides this baseline PLC. It acts as a PLC coordinator, but it also acts as a 2.4 and 5 gigahertz Wi-Fi access point. And it can be useful in some houses where Wi-Fi coverage is not that good, to have this extra box placed in the strategic location to provide support for your Phantom system. And we also had to deal with different constraints. So it's an embedded product. So you may ask, why didn't you use whatever tool is available and everything? So we have constraints. We can guarantee topology. We can do a bunch of things. But we also have very limited resources in terms of CPU and RAM. So a lot of projects are being built using modern technologies, which not always apply to the embedded world. So we strongly prefer development and tools in C and C++, because we know the runtime, it's very predictable, and we also know the tooling and how to debug situations when it's that's especially in the embedded case I talked about. There's also a bunch of licensing issues. You can just use GPL or LGPL code in a product that you ship. It's different from hosting this code on your infrastructure because it never leaves your company, basically, so you're not distributing it. But if you put that code in a product and you sell that product, it's distribution, and you have to deal with all types of legalese, and you have to make, sometimes you even have to open source complete parts of your stack. You can do static linking. You have to run external processes. It's a nightmare. So there weren't really easy to find solutions to address most of our problems. So that's why we had to come up with what I just described. And we learned a lot in the process of building the system. One is design for failure. I guarantee you that failure is going to happen. Error is a normal case in your application. So we made an error in the very beginning, which was to have an error management system based on integers. Integer return codes, error codes. And this was from some, I don't know, ideology that exceptions in the C++ runtime are very expensive and too expensive for the embedded environment. That's not really true anymore. In the normal case, you don't pay extra for using exceptions. But in the exceptional case, which is exceptional, you're going to pay a small extra. Use standards as much as possible. So typically, we design a whole UDP discovery system where stuff just existed for it. So Bonjour, for example, or multicast DNS is perfect for discovering hosts on the network. IPv6, we use IPv6 in a new iteration of our system. We don't have to have DHCP and stuff like that to configure hosts. We can just use link local addressing, which comes naturally with as soon as you activate IPv6 on your hosts. in the home environment, multiplex as much as you can on TCP connections. Don't just open a bunch of TCP connections. It's going to be really slow to just get those connections open in the first place. And use UDP for time-critical operations. So the example I had in mind is the user turns the volume on the volume knob on its remote, and it takes an infinite amount of time because it uses TCP, and there's some retries, and the information comes like maybe 10 minutes later. So he's listening to music, and at some point the music just go way up or way down. It's incomprehensible for the user. So just use UDP for that type of things. And the last thing I have to say is that timeout management is really, really hard. It's really not easy to guess and define what a proper timeout value is. It varies from one installation to another. So yeah, avoid having to deal with timeouts. And the example I had with the WhatsApp daemon, where you can just be notified that a service was killed, is a way better solution. So I took a little bit more time, but thanks for listening. And if you have any questions, just ask.
We are going a little bit over time, so we will take one or two questions, but then we have to move right on to the next one. Okay?
Sorry, guys.
Maybe someone in the middle will catch. Let's see what happens.
Hello, thank you. How do you handle software redundancy? Like when a server on Amazon goes down, and maybe it goes down to the point where I can't even SSH to it, I just order a new one. And you have customers unplugging the device at the very, very wrong time and stuff like that. How do you handle that?
Basically, it's in the aggregation phase I talked about. So the application which relied on services from that device is basically going to have to adapt. So for example, if you're a source and you were streaming to that device, which was a renderer, you just have to figure out that the renderer is no longer available and just stop trying to send audio to that device and just wait for it to maybe come up at a later time and just reconnect and start streaming to it again.
And how do you rescue that device?
What do you mean?
I mean, if let's say the user unplugs it when you are doing the update, the software update,
yeah.
It doesn't boot anymore. Do you have some solutions such that Mender or Resin, for example, stuff like that?
So we use in our bootloader. Basically, we have a boot count. If we can manage to boot into the normal Linux for whatever amount of times, we just move into the rescue mode, and in that rescue mode, you have to plug the device to through the Ethernet because you don't have any network configuration, and it's going to try and go fetch the latest update from our servers and just apply it locally. So that's how you rescue a lost dead device.
Yeah, thanks for the talk. I was wondering, how do you, because it's a Nodo file device, so I guess latency is a big issue.
Sorry?
I guess since it's a Nodo file device,
yes.
Latency is a big issue.
Yes.
And so with the whole RPC and the containers and the different levels of abstraction, I was wondering how you deal with this.
So latency is really an issue only on the audio path. Like if you have latency in establishing the connection for a renderer to become available to a source, for example, it's just from a user perspective, it's going to be this renderer is not playing for whatever reason, it's booting up, it's trying to connect to the network. But as soon as it's connected and you actually have this link, we're going to start sending audio to it. And the really critical path is this audio path. We have to deliver the audio samples within a limited time frame if we want to stay synchronized with the other devices. So if the audio arrives too late, we just can't play it, and basically the speaker is going to be dead and appear not to be playing. But that's the type of thing that customer support helps our customers debug. Yeah. Thanks a lot, guys.
Ça allait pour le temps. Je te laisse le mettre dans ta poche.
Dans la poche directement.
Et je te ferai un petit signe si tu dépasses.
J'ai mon timer de toute façon, mais... Okay. Hi everybody, thank you for being here. I'm Alban. I work as a software engineer at Criteo in the scalability team, mostly working on service discovery, hence the load balancing and metrics. Let me tell you the story of a journey, the journey of Criteo from the monolith to services with client-side load balancing. I'll share with you our failures and success we got on the path. To begin with, let me give you a bit of context. To display an ad, you need basically 4 applications. One to track the users and get a profile. One to place a bid, to set a price for an ad space for a given user. A banner renderer and a click counter. A long time ago, those 4 applications were basically a big monolith. And on one side, we had the internet, the users, and on the other side, we had the applications. They were, between them, we had an F5 load balancer that was doing just round robin on a pool of servers. That was quite simple, quite efficient, but not so scalable. Because after a while, we were no longer to work with those mega monoliths. They became too complex. We had a lot of spaghetti code, and we were not able to release anything for around 6 months. That's when the idea of splitting them into services came, to make them easier to understand, easier to maintain, to have a better ownership of the code. And with that, now we have a pool of servers that need to talk with another pool of servers. This is how we first introduced HR proxy, because F5 are very expensive. HR proxy runs on a regular server. It's open source. It's efficient. At this time, we had gigabit links, so it has 1 gigabit link input and 1 gigabit link output. It's a bit better now, but at this time, we had only that. And this is when problems started to rise, because for our request rate, around 200K requests per second at this time, and the size of the payloads, we needed much more bandwidth than we actually had. So we started to optimize. On one end, on the hardware side, we did link aggregation. So we bound several network interfaces together to make them act as one. So it increased the bandwidth available on this virtual network interface. And on software side, we did compression on the payload. So we lost a bit of CPU, but won a bit of bandwidth. But we had to wonder, do we really need this HR proxy? Because even after those optimization, we needed around 45 HR proxies per data center, which we considered to be too much. And HR proxy was either a SPOF and a SPOC, so we considered completely removing it. And this is how client-side load balancing appeared, because as opposed to outside traffic, we control both ends of the pipe, either the client, it's our code, and the server, it's our code too. So nothing prevented us from providing the list of all the servers to all the clients. Let's talk about the algorithm. And to begin with, I'll give you some figures. When we introduced it, we had around 250 clients and around 300 servers. We considered that the Cartesian product of the client times servers was a bit too much. So we thought we couldn't open so many network connections. So we started with the first intuitive idea. And at this time, we were so happy to have so much traffic that we thought just the volume plus the randomness would balance auto-magically things. So a client chose n node randomly in the server pool, and it did round robin on them. As a result, we noticed that some servers received much more traffic than others. The variance was huge. As you can see on the graph, you've got here the traffic rate per server. The average difference was around 100% between the least loaded and the most loaded server. So for scaling, it's a big issue because we had to scale for the worst case. So many servers were underloaded. So it was a huge waste of resources. So we moved to a more deterministic solution. We used window round robin by giving to the clients the knowledge of their position in the pool. And so the first client could take the first n contiguous node and do round robin on it. The next client take the n following, and so on. It's good overall. We reduced a lot the variance, but not enough. A perfect graph will be a single line, because that would mean all servers receive the exact same amount of traffic, so they are perfectly balanced. And by the way, this works fine when all servers are up, but when one is down, the remaining traffic is rebalanced just on that small pool per client, so the traffic increase for the remaining nodes, and at some point, everybody dies. I told you we didn't consider doing full mesh, meaning making the clients talk to all the servers, but we didn't try when we decided that. So we actually tried, and the fun thing is that it worked. Actually, it worked only for a while, because when we reached 1,024 servers, our routers crashed. It's a funny number. And it's also, by default, the size of the ARP cache. It has 1,024 entries. The ARP cache does the mapping between an IP and a MAC address. So when this cache is full, it's flushed. And for every request, the client had to query broadcast, hey, who's got IP 1, 2, 3, 4? And it got the answer, is John. And then for the next IP, who's got IP 1, 2, 3, 4? The cache was flushed, so we had to rebroadcast the thing. And this is how we crashed our routers. The fun thing is that we had the same issue with our Linux machines around 6 months ago, and we patched them, but not the Windows servers. So we did it. Now it works. After a while, we bought some more servers, a new generation of them. So the new one could handle much more traffic than the old ones. So what should we do with them? Should we give them the same amount of traffic as the small one and waste resources? Probably not. This is how we introduce the weighted round robin, which has the same advantages of the regular round robin. It's still very deterministic, but we had to determine weights for those new servers. It's empirical. We had just to measure what traffic they could handle. Those weights may change over time, and we are not sure after each release that those weights are correct. To give you the result, this is a graph from yesterday. You can see that the traffic rate is almost aligned for each generation of server. By measurement, we determined that the new server needed a weight of 30 and the old needed a weight of 20. And if you look at the average figures, the old server receives around 2/3 of the new generation traffic. Let's move to another topic, which is health checks, because clients need to talk only to healthy servers. A long time ago, not so far away, we had an in-house service discovery system which had the knowledge of all our nodes for a given service, but had no idea about their health. So every client had to perform a health check on every server it targeted. So as we're doing full mesh, it made a lot of network traffic, plus a huge CPU usage, so it impacted performance. Since we migrated to Consul, Consul is able to perform its own health checks on servers. So now we've got only one service performing health check on all the servers. And the clients are able to query Consul to get only the healthy nodes. And so everybody wins bandwidth and CPU. This is where the story stops for today, but it's a never-ending story because it's constantly evolving. For instance, we're currently working on adapting the weights of the server according to the latency. Somebody working on that topic is hidden here. I'll let you find him and talk with him. Thank you for your attention and feel free to ask any questions.
Be careful.
Thank you for the presentation. One thing that I didn't get at the beginning is why was the round robin, the first round robin implementation, not balanced correctly? The very first one, it was apparently the worst
The
case.
random subset?
Yeah.
Actually, we've got a pool of servers, let's say 100 servers. A client takes randomly 10 of them, and it does round robin on it. So it picks randomly some servers, and we think that randomness makes the balance, but actually it did not.
Okay. Do we know what's the cause of that? Is it because the randomness is not so random, or have you investigated that? It was just a question.
I didn't work on that, so I've not all the context, but probably that the volume are too small to have a real effect of randomness. When we've got 300 servers and we take only 10 of them, it's not so random.
In one of the latest implementation, you were speaking about health checks done at the client level on every single servers. Did you try to just not do health check, but remember that the last call was failing? Not be proactive, but more reactive on the health checks?
Honestly, I don't know.
Okay.
Any more questions? Thank you.
Okay, before you run out, just thank you very much, everybody, for coming. Next tech lunch in 1 month, the subject will be horror stories. So if anybody has a horror story about something going wrong in production and how you fixed it and you would like to speak, we don't have speakers yet, so get in touch. Also, we're hiring, and some of the jobs are posted. You'll see them on the way out, but obviously you could see everything on our website. You can come talk to any of us if you want to find out more, and have a great rest of your day. Thanks.